completing the joint unit, and there's a few seconds. I just didn't want to rush and squeeze it in just because I want to talk about it. I'll give you a little background on both of those diseases. And then that concludes all of the information for the exam on Wednesday next week, the 29th. So I did send you the review recording. I'm sure you if you didn't look for it, then not everybody's going to be sitting there, Sunday evening, wanting to listen to my voice excessively. It's there, but all good. So I managed to get that done. It's maybe took me about 35 minutes of talking time. If you have any questions, just direct them to me, email me. I'm around, come in and see me, whatever. If you have a question in class, I'm sure everybody would be interested in the answer as well. So much for the introductory remarks. Here is the end of said chapter, the last two slides of joints. And basically the two slides are very straightforward. They're gout and Lyme disease, which is interesting because it never used to be included, but we know more of it. And it's more of not the initial phase as much as the chronic phase, I would dare say. And again, I have a fair amount of experience in both of these. Gout's interesting. Gout is a metabolic disease caused by an excessive amount of a chemical called uric acid. As your body chops up and recycles cells, the nuclear material, without going crazy about it, those adenines and guanines, they're called purines, and that UR is where uric acid comes from. So we can tolerate a certain amount in our bloodstream all the time, but we have to get rid of it. So it's not something we want to have floating around in the bloodstream. So and that's true for a lot of waste products. When you get into kidney, you're going to see the same thing. There's a lot of waste products that basically are similar that as long as your kidneys are doing the job, they're getting rid of most of it. That's something for AP2 with the physiology of the kidney. It is certainly more common in men up until roughly age 55 to 60. I've treated a ton of it over the years because it's more common in the lower extremity than anywhere else. And literally think of a hot foot. It's red, hot, and inflamed, and it usually can affect the foot's the most common area, then the elbow. But as people get older, it can occur almost anywhere. The uric acid, when there's an excess amount in the bloodstream, forms these crystals that settle in joints. And unlike salt crystals, they're needle-shaped dagger-like crystals. If you look at them, if you Google them and look at them microscopically, and they're so large that the white blood cells can't swallow them and they explode. And effectively, they set up this vicious inflammatory cycle that goes along with it. So, and again, Egyptian hieroglyphics showed this. So it's not something new and modern from things like that. They used to think it was all about diet, and it was the rich man's diet and blah, blah, blah. It really has more to do, if you study it in metabolism or in endocrine diseases, which you probably won't. It probably has more to do, we think, with a defect that people have, sometimes hereditarily, with not being able to get rid of the uric acid, having an enzyme that basically breaks it down efficiently. And these are all reasonable treatment things. It's a pain in the neck. The thing is to understand that if it's not taken care of properly over time, these crystals that begin to accumulate in organs, and it can be fatal in late stage. That's really all you really have to know. The big deal is the uric acid, and the big deal are the crystals, and the crystals really provoke, they're so nasty inside of joints that they create extreme inflammation. So much for the gout. Last one, Lyme disease. If you're doing micro with me, which I'm guessing probably 2/3 of you will, okay, we talk about Lyme disease more extensively. And when I do my unit on diseases, this is the most common vector-borne disease in the United States. A vector means something's carrying it to you. Rabies could be a vector. West Nile virus, mosquitoes. The mosquito is a vector. Vector is some other animal or insect that carries it to you. This is number one on the hit parade. We have a ton of experience around it here because part of the tick's life cycle involves deer, particularly the white-tailed deer of really around this area. So it has to do with where ticks live and where deer live, and I go into chapter and verse about this in micro, which is more apropos. It starts with a skin rash. It's very distinctive. It's called a bullseye. It looks like a target-shaped rash that you can see, and very often it begins to bring on, feeling lousy, flu-like symptoms, and down the road, it has a strong predilection. There's like three, pardon me, it's bacterial rather, and three phases that begin to, I'm trying to think the right way to say it. They start sort of like this, but when the rash goes away and kind of the flu symptoms go away, bones, joints, muscles, nerves, there's quite a bit of it. As it spreads through your body, it's an immunological system. So it used to be classified as a skin disease because it started with a rash. Now we classify it as an immunological disease. And your immune system goes nuts and starts attacking healthy structures, not unlike what we see with rheumatoid arthritis. And I mean, I'll go into it in some. The treatment, if it's discovered early, is antibiotics. The treatment, if it's discovered late, is antibiotics. It's just a matter of how long, and the sooner you get to it, the less likely, because there can be permanent damage. People can die from Lyme disease. And how common is it? When we had, not the 2020 year, was it 2020? Yeah, I think it was 2020. I think it was during the first big COVID lockdown, and it was during that summer my wife got it. Because what were you doing? You weren't going anywhere. You were just taking long walks and keeping away from everybody else. And we live in Cranberry Township, and we live in what's called the Woodlands area, and it is deer central. You see them all the time. And so all of a sudden she goes, this is killing my side's killing me. I think I got a bug bite. And she sort of slides that part of her shorts down, and I see this big red rash. And right after that, it started to form the bullseye. I mean, she went, in those days, I couldn't even go into the urgent cares. Because they wouldn't let the person in. And whoever the physician or the nurse practitioner saw it went, Lyme disease. In about a 3-week course of antibiotics, and fortunately no after effects, quite early. So it's common. It's a question of getting it early. So that's it. And those are the things you have to do. There is not a Lyme disease question on the exam. There is a gout question on the exam. So fair play. In micro Lyme disease questions coming your way. It's got a great name for the bacteria. Bacteria have wonderful names. Borrelia burgdorferi. I didn't name it, but I can remember it. So much for that. Bye. See you. New material. Ladies and gentlemen, the tough stuff is coming now. I just sent you this PowerPoint. There's all sorts of goodies. After we get all this initial stuff out of the way, we start looking at this kind of stuff. You're going to see, as I'm scrolling through, we're going to look right down to the microscopic level. We're going to look at these banding patterns. We're going to look at all of these things called sarcomeres. We're going to look at that kind of stuff. And then we have a variety of animations as I scroll through it. Have fun. Okay. Earlier, I thought we were going to have like 15 people, but thankfully, I'm reinforced by seeing people there. So the people who are not here, I'm talking to. If you know them, tell them to get here. Time's coming. You've got at least a 2.5-hour nugget of free time on either Tuesday or Wednesday now. Use it appropriately. Don't look at me like that. Muscles. This is not the muscles thing that you did in lab where you play name that muscle. Okay, there'll be a few names of muscles in here to show you how the muscles work. Postural muscles are a certain kind of muscles. Power muscles are a certain kind of muscles. There's fast muscles or slow muscles, if you didn't know that. But this is how muscles work. And this is where we're going to get our real exposure to what's called the first time we see the interaction of your two control systems. In this case, we're going to look at the primary one for fast, the nervous system, and how it impacts muscles. Muscles, half of your body's mass, the weight of your body is muscles. Bones aren't that heavy. Muscles are. And again, this is where we see energy transformations. And indeed, one of the areas that we look at is called excitation contraction coupling. We're going to marry the firing of the muscle, the excitation of that muscle, into making it contract and shorten. And all of that has to do with transforming energy into different forms. So there's a lot of energy transformations that are used here, and sort of, implicitly in that discussion is the utilization of ATP. So here we are, transform chemical energy into directed mechanical energy, which is capable of exerting force. I'll buy that. I don't really care so much about the definition, but it's the energy transformations that are there. So we have to look at the different kinds of muscle, how they work. Basically, and we spend and most of this chapter is dedicated to skeletal muscle, the muscles that you think of when you're moving muscles. You do a whole heart unit in AP2 where you talk about cardiac muscle, and effectively all of these wonderful hollow tubes, blood vessels, genitourinary, digestive, respiratory, all of these interesting tubular structures are smooth muscle. And even though I will mention it in passing here, we only do a little bit of it here. So the big focus point is skeletal muscle. It's there. So, and there's a lot of these interesting prefixes. So we have myo and mes and sarco. Sarco typically is when we get down into the cellular level, even the molecular cellular level. So cytoplasm becomes sarcoplasm. Sarcoplasmic reticulum is another name for endoplasmic. Sarcolemma is actually the actual membrane. That's to say, lemma is another term that you see in Latin for membrane that are there. And myo and mes, myo is pretty easy to think about with muscle, but mes is also, depending on the area we're looking at. So here's skeletal. The unique thing about skeletal, it is voluntary, meaning you decide to move that muscle. Not talking about reflexes and things like that, but when you move, you've made the decision to type whatever you're typing now, or write whatever you're writing now, or whatever you choose to be doing, and utilizing your fingers, your eyes, whatever. Cardiac and smooth muscles, by definition, are involuntary. So they are not directly under our conscious control. So only skeletal and smooth muscles are elongated and referred to as fibers. Cardiac is an oddball. Okay, that's there. So you understand, when we start talking about a muscle fiber, that is actually the cell. This is your first taste of seeing how some cells are pretty unusual. This is sort of, again, a confluence of multiple cells and can be as long as a foot long. An individual cell. So you imagine it'd be very, very thin, very, 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 microscopically thin, but quite elongated. So you're going to see the way that it's packaged very shortly. We talked a little bit about how things attach to bone. This is another good example of it. And the thing that's not only being voluntary, what identifies them is visible stripes. So another name that you will often see referred to this is striated. So skeletal and striated muscles are interchangeable terms. And notice I highlighted the word visible stripes. That means visible microscopically. They erroneously call smooth muscle, and even this PowerPoint will say, well, it doesn't have any striations. It doesn't have any visible striations. Okay? So understand, it's a matter of whether a lot of times it's whether we can see things or we don't. We'll name them. It's like that stupid lacuna they keep talking about. Well, it's got a hollow chamber. No, it's not. But, that's what they saw, so that's what they named it. A lot of times it's not a big issue. It's just, I have pet peeves all the time. So voluntary muscle, okay, is another thing because we can use it consciously controlled. We can move them real fast, but they tire easily, but there's a tremendous amount of strength. So you're going to see the implication for a lot of these is strength and endurance. Okay? These are very, very strong, but there's not a ton of endurance. Okay. If you want to think of smooth muscle, it's our muscles in our gut are being used all the time. Right now, they're busier than any other time. but there's not a lot of oomph. Most interesting one of these is cardiac muscle because it's that beautiful mixture of endurance and strength. You're going to see it's striated, but thankfully it doesn't tire. And you'll hear me say this a whole bunch. It beats more rapidly than once a second every second you're alive. Keep going. I like it. Okay, so the key word: skeletal, striated, and voluntary. Cardiac, only in the heart. Visible striations implies power. Involuntary, and then we'll get into the rate and all that nonsense, but that mostly is AP2. And then lastly, smooth, we talk about a little bit. Hollow organs, think of, again, blood vessels, genitourinary tube, bronchial tubes, digestive, etc., etc. They are striated, just can't see them. That's me. Don't worry, I'm not going to ask you that. And they're involuntary. And normally when they say visceral, that's a name for your viscera or your internal organs. Think of it that way. With the heart being somewhat unique in its placement. That are there, they show you some neat pictures. And here, I'm not doing the microscopy unit about these things, but so I'm not going to sit there and spend a whole lot of time about that right now. Talk a little bit about the spindle shape and skeletal. And I mean, so they're very distinctive microscopically, as distinctive and different. What do they have? They're excitable. Okay. That's the whole thing. Remember, and this is part and parcel of what I commented on in that review recording, that resting membrane potential. All cells have it. Okay? But these are cells that can change rapidly across the membrane. And that's really what a lot of the physiology is about. And by that point, we call them excitable or responsive to stimuli. So when we stimulate these, we get changes across that membrane, and that eventually is going to, and rapidly, eventually is probably a poor way to describe it, relatively rapidly is going to make that muscle contract. So it will shorten. Muscles don't flex per se, they shorten. Their shape determines basically what happens and what they're attached to. But effectively, they shorten. If they're shaped, a biceps will bulge in the middle because of its shape. It's just contracting, sort of contracting and widening in the process. That's a lab type thing. That's more of the gross appearance. That's when I talk to my anatomy lab. We go over the different. Maybe you did those fusiform, parallel. Is that ringing a bell from lab? And a little bit. What's the longest muscle in the body? Pardon me? Thank you, sartorius. Why is it called the sartorius? You see, this is the kind of stupid trivia I will never ask you, but it's great. I love this. Have you ever heard the expression sartorial splendor? Someone who's the opposite of me, wears very, very, Dr. Robbins, wonderful clothing, very fashionably dressed. He's a sharp dresser. Did he do any of his labs when he came in like in slippers? And he did wear those labs. So he's more confident. I just wear the same old shirt and the same old pair of pants and just recycle them. Sartorial splendor is somebody who's neatly dressed. They call it the tailor's muscle. In the old days, tailors, before they had sewing machines, would sit kind of, with their legs curled in front of them. To be politically correct, Native American style. Okay, we used to say Indians. Don't say that. Native American style, and like that, and that sartorius muscle would basically flex the hip and flex the knee because of the way it's attached, and it would be very prominent. So they named it was the tailor's muscle. People see, you learn something new every day, and that is totally useless. I would be unusual to find a crossword puzzle where that, how many ever letters it beginning with an S is known as the tailor's muscle, might help you. Extensibility, you can stretch them. Elasticity, recoil, pretty straightforward. Okay, they produce movement, we'll buy that. All of those things. Maintain posture, buy that. Stabilize joints, okay. Not going crazy over it, but it happens. And they generate heat. Remember, we talked about that. When you shiver, you're generating heat. That's involuntary muscle contraction, but they're skeletal muscles. And the motion, shivering versus sweating, negative feedback deal. and all these different things that are part of this is more of the structure. You probably got this in lab. It's a review. We know it all has in classic anatomy. You talk about the nerve supply and the arterial supply. I do not know if you do that or if you will continue to do that going on forward. Okay. And they have a huge amount of oxygen and nutrients and huge amount of waste products because of that. So that's the really unique things about muscles, and we'll get to that when we start looking at energy usage and talk a little bit about aerobic usage and anaerobic usage. And that's really important, particularly going forward when for many of you going into clinical fields and you're doing rehabilitation or you're talking people who have a heart attack, you begin to understand a little bit about how they can either prevent or at least treat, be part of the rehabilitation process. The connective tissue. Okay, this is the terminology part that's a little bit important. You're going to see this recurring pattern of threes. We have lots of things in threes. So in this case, and you're going to see the same thing with the nervous system as well. So when we're looking at what you and I call a muscle, okay, you have what binds that muscle and gives it its shape is dense, irregular connective tissue. Not unlike the periosteum, not unlike the deep dermis. It surrounds the muscle, and the fascia is another layer of connective tissue that sort of governs it. Well, did Dr. Robbins, when he did muscles, did he talk about things like compartments and things like that? I mean, it's more of a concept when we're looking at kinesiology and the way muscles work. But there's fascia, there's tissue that typically additionally binds the muscle to bone. So you have fascia in your thigh, you have fascia in your arm, and then underneath that is this dense connective tissue. So if we would remove, let's say, post-mortem to look at a particular muscle, you would have to separate this dense connective tissue. The fascia is a little bit more, a softer, more pliable tissue with that dense, irregular connective tissue, pretty sturdy. So, and the analogy to that, I'll show you. And then we'll talk about fascicles, the way that it's bundled. That's again connective tissue, not as dense. And then endomysium is very delicate. That's around the individual fibers. And in muscle like this, the term fiber and cell are interchangeable. This is where things are going to start to get confusing. We're going to talk about fibers, which are larger. Then we're going to talk about fibrils, which are smaller. And finally, filaments, which are smaller yet. It's really very difficult at times to understand. Voila. So here we are, whatever muscle that is. Let's say it's a big old hamstring muscle. Okay. So that outer layer is the epi. Epi is outside, like the epidermis. Okay. Another thing that you see it if you get a piece of meat. Okay. It's stuff that we call silver skin. It's not good eats. It's the kind of stuff that you want to trim off, or at the very least, you're not going to be consuming after you cook it. It's quite unpleasant. And then if you look, we call this the marbling pattern. So the way they slice meats is transversely. So this is the elongated piece. And then if you would slice it and look at it, in those big boats that they have out in the grocery store in the refrigerated section, that's what you're seeing. And that's how you be the difference between a sirloin, between a T-bone, a porterhouse, a strip steak, a filet mignon, etc., etc. Okay, it's all about, and the marbling pattern is how fatty it is. And that's why you pay a ton of money for prime beef, or if you really want to go top shelf and you want to go Wagyu beef. Okay, which is, in Japan, they massage cattle before they butcher them. I'm a foodie. This is what stuff you learn. Don't go there. They're just going to look at you like you're strange. So if you pull out one of these individual bundles, it is a fascicle. Nerves have the same arrangement. The difference with nerves here, the blood supply is on the outside. In nerves, the blood supply is in the middle. We'll get to that down the road. And lastly, and again, it's a repetitive pattern. So here's a bundle filled with additional stuff, and they are bundled. But now we're getting delicate. This is the individual fiber or cell. It's a unique, complex cell. That's why when it's injured, it dies and it's replaced by scar tissue. We can't make any more. Whatever you're born with, that's your initial complement. You can make them larger, you can make them thicker, but you can't make more. And that is the endomysium, and it's multicellular. And these little rods, flexible rods that are in there, as you will come to learn, are fibrils. And we're going to pull out one of those rods, and then we're going to turn it on its side, and then we're going to look at the structure within those flexible interior rods, which are filaments. And that's how we begin to understand the muscle. Are you getting an idea why I basically almost make this a standalone test? Because it's going to drive you, unless you're really on top of this, crazy. So again, I use the word attachments versus insertion and origin. Don't bother with it. That's lab to me. The whole movable but not. And the way it attaches, it'll either go directly into the bone or indirectly with a tendon or that neat thing called an aponeurosis, which I hope you did in lab. Ringing a bell? Aponeurosis, plantar fascia, ligamentum nuchae, Galia aponeurotica. You can, no. Frontalis, occipitalis. The reason you can wrinkle your brow, they're both attached to the sheet-like structure called the Galia aponeurotica. Your plantar fascia, that bowstring across the bottom of your foot, muscles attached to that. It's okay. We're in a good mood. See, it made up for the Steelers' defense. Haha. Man United finally beat Liverpool in Liverpool. And I'm happy. I don't see any real soccer fans in here. I digress. Voila. So here we are. The epimysium containing bundles of, this is the part for you to know, bundles of fascicles. Each fascicle has bundles of fibers, individual cells. Okay, and now that that endomysium is a bit of loose areolar or loose soft connective tissue that surrounds the individual cells. If you peel that away, underneath it is the membrane to the individual fiber or cell. The name is sarcolemma. That's the muscle, quote, muscle cells membrane. And then what we're going to do is we're going to pull out these individual fibrils and actually look at them. They're there. So the muscle fiber is an elongated, multinucleated cell. It has banded, striated appearance, which you will see, and is surrounded by epimysium. So the skeletal muscle fibers are long and cylindrical, multinucleated. Okay. The sarcolemma is its plasma membrane. They're changeable. We no longer have, quote, cytoplasm. We have sarcoplasm. Certainly it's similar, but understand this is just filled with protein. Muscle basically is protein-containing rods, masses of protein, tons of mitochondria because it requires a lot of energy. And you're going to see that red color comes from an oxygen-containing protein called myoglobin, where in your bloodstream, the oxygen-containing compound is hemoglobin. They work similarly, but a little bit differently. We're not going to go into the ins and outs of molecular biology. Go next door and you can hear my colleague teaching. That's her job. So, and it contains glycosomes because glycogen is the energy supply. And the myoglobin is for oxygen. That also imparts the red color. So if you're, so the difference between red meat and white meat, they all have myoglobin in animals. Okay, for those of you who are, I'm explaining to you, assuming that you're a vegan, this is the explanation. So if you're not used to it, when you talk about red meat and white meat, the difference is how much myoglobin there is that's here. So some animals have a relatively limited amount, and it's mostly white appearing meat versus darker red appearing meat. It depends on the content of myoglobin. So in poultry, so the breast meat is white meat, doesn't have a lot, and the muscles that are used a lot are the legs, they have much darker meat. We get a lot of use out of a Costco chicken. That ended up with a couple of meals out of that. I also make chicken stock out of all those. You make your own stock, don't you? Yeah, that's what you got to do. Hey, you bought it. Don't throw anything away. It's good stuff. So all of these, the modified organelles, and that's what they are. The fibrils are an organelle. They happen to be where the contractions take place. The sarcoplasmic reticulum is a unique, smooth endoplasmic reticulum and contains a ton of calcium because that's what makes the muscle work. You see this down the road. And interestingly, the membrane produces these interesting ways of conveying the electrical signals deep into the interior of that muscle fiber, and they're called T, and the big T stands for transverse. I will go over all of these things innumerable amounts of time. But what I'm trying to get, the point I'm trying to get across repetitively is how complex this is. So densely packed rods, single muscle fiber can have thousands, 80% of the muscle volume. So and this is just a package of protein. So it's extremely dense. I mean, muscle is basically all protein with the exception of the stuff it needs to make it. The way it moves are these proteins changing shape, as you will see. And we go into all of this. And thankfully, why I really love this particular PowerPoint, it's got great animations that explain in detail how it works. And because I just sent it to you, you can listen to it a zillion times. So striations, the individual units that we're going to study. So this is one of the things you begin to see now as you move into much more function. We're looking at nerve function and muscle function as part of AP1, and you get into all the other organ systems after that. We basically look at a series of repeat units. We look at the smallest unit. What this does, now we can just sort of make it into all the others. We get to the kidney. They have millions of repeat units called the nephron. If you understand one, you understand all. That's kind of the point I'm driving. You see how the digestive system works. You begin to get an idea of the way it's arranged. You look at the arrangement and you understand how it works at different levels. So you begin to understand the way that really studying this works. Years ago, before the age of molecular biology, we didn't go into it in such detail. But a lot of what many of you are going to do and the fields you're going to go in are based on this, and you're going to need a certain amount of understanding to understand what happens. What's the difference between someone has a spastic muscle where someone has a flaccid muscle? And what type of things are the side effects of certain medications? Or what if all of a sudden they develop something because you just gave them an injection of something, what am I going to do about it? Just how serious this is. And depending on all these, there's so much to it that are there. So striations really are a banding pattern. They have to do with where the proteins overlap. So it's really not magically that somebody drew stripes inside of your muscles. It has to do with the proteins. And when we see things visibly, it's a matter of, does the light go through it or does the light bounce back? That's basically why we can see it a particular way. The sarcomeres are these individual repeat units. They use a pretty reasonable analogy. It's like a long train with a series of boxcars. And the boxcars are identical. And what happens in one boxcar will happen to the next and the next. And so it's the accumulation. It's like all those little joints I was telling you about in your back. And all those, they create a lot of motion. Same thing here. If one of these tiny microscopic structures contracts, all the rest of them contract. And additively, we get a certain amount of shortening of the muscle. And we'll look at the individual fibers that do this shortening. They're called myofilaments. And indeed, we'll look at the composition. That's where you're going to hear about things called actin and myosin and titin. There's what to learn about in this chapter. So voila. So here we are. Next step on the hit parade. Here's the microscopic anatomy. Here's a muscle fiber. How do I know it's a fiber? We saw the illustration before. Here we have, imagine that endomysium is gone. We just moved it away to get a better view, and we're looking at the sarcolemma, actually the cell membrane, multiple nuclei. Here we're going to pull out one of these additional flexible rods, which are called fibrils or myofibrils. And you see this sort of striped pattern that they've drawn in color here. Each one of these little guys here is called a sarcomere. That's the part we have to understand. So the striation or stripes, okay, from each repeating series of dark and light bands along each myofibril, that banding pattern. So basically you have an area you're going to see a light zone and a dark zone, a light zone and a dark zone. They give them names. You will never get this wrong. The A band is dark. There's an A in dark. See? The I band is light. There's an I in light. There may be no I in team, but there's definitely an I in light. They always tell you that in sport. There's no I in team. My eldest was a goalie. There's an I in goalie. So I bands lighter, A bands darker. And then I'll show you what the H zone and the M line is. They're big on letters that are there. And my favorite, the Z disc, because it zigzags. So you're going to see all of these types of things. So this is what you do need to be a little bit familiar with. And no, we're not going to label the diagram. This is kind of what it looks like. I don't get a lot out of this particular illustration. That's there. You can see the nuclei are there. And basically, if it's either light or dark, I'll buy that. So microscopically, under a light microscope that you would use in lab, pretty easy to tell skeletal muscle. It's one of those easy kind of slam dunk kind of microscopic things. Our idea here is to look at it molecularly, submicroscopically, the smallest contractile unit. That's really the functional unit. Just like the functional and structural unit of bone, we were looking at that osteon that was there. If we understand that, you basically understand where bone gets its strength and some of its flexibility. Here's the same deal with the sarcomere. So we take these ultra microscopic structures, okay, and it'll easier to show you about an A band with half of an I band. What do you mean by that? And the Z discs. And again, this whole idea of boxcars works. This is a better way to look at it. So this is, again, maybe it's 6 inches long, maybe it's an inch long, doesn't matter. These are all very, very tiny. There could be thousands of them lined up. The boundaries of the sarcomere are the Z discs. They are proteins that attach to what you will come to see are the filaments. Where they overlap, the blue and the red. Okay, these are two different kinds of filaments you will come to see. Where they overlap, that is where they are dark. When something overlaps, it's difficult to see. Okay, the light doesn't go through it, so it appears dark when we look at an electron microscope. On either side, and this is what I mean by half of an I band, there's an equal amount at rest. And this is when we're going to look at one of these contract and what they look like differently. There's an equal amount of just this blue protein, which you're going to come to know is called actin, on either side of the Z disc when these fibers are at rest, not contracted. And you will see that is the so-called I band. So that's where they come. There's half an I band on either side of the Z disc. The A band is in the middle, and then you have another half of an I band. What effectively makes this is you have thick fibers and thin fibers. So each thick fiber has you see it better. They drew it better than I do. Hexagonally around it, but there's a whole bunch of them comparatively speaking. And so maybe you'll have another one that's over here, a thick fiber, and then you can turn around and draw, the other dots associated with it, one over here and here, here and here. And effectively, there's a 2-to-1 ratio of, and this is important, of thin to thick that we see in skeletal muscle. And down the road, at the end of this unit, you're going to see it's about 12 or 13 to 1 thin to thick and smooth muscle. So it's there. That's why the striations are there. You just can't see them. There's so many thin ones there. And you'll see that part of the illustration here. If you look at the tail end, you can see that pattern drawn better than I am. The red would be the thick, the blue would be the thin. You can see them hexagonally around them and how they're all intertwined. So it's hard to do. It's something, some people can learn it, some can't. It's almost like I can look at the structure here and sort of magically, mentally turn it around. It's called spatial relation. It's not easy to do. Some people have it, some don't. I was lucky I had it. It's one of the things with some of the admission tests to different medical professions we had a whole thing on called spatial relationships. It's like one of those things they show you, like a geometric structure, and they have 4 of them turned around, upside down, right side up, and say, which one is the same as this? My luck, I was good. So the individual little guys in there are called filaments, thick and thin. Orderly arrangement. The big players, the thin ones, are actin, a name that you heard before. In the cell, those are the microfilaments. And myosin. They are the thick ones. They're actually proteins braided together. We've heard about that before. And they are motor proteins because they move. It's their changing shape that creates motion. That's myosin. And they are the big players within the sarcomere. The actin is thin, and as I showed you before, it's across the I band and somewhat into the A band. That's the overlap. And they are anchored to the Z disc. Effectively, what happens, it's as though my arms are the I bands. They're anchored to the Z discs. They basically get pulled toward the center when your muscle contracts, and it's as though the sides get pulled in closer and closer. It's one of those rooms in a bad sci-fi movie where the walls kind of come in close to you. It's Indiana Jones, Temple of Doom, not Temple Bethel. That's a line from Spaceballs, the movie. I know. It's okay. Like if you went to like Disney and you went to one of the stretch rooms for the Haunted Mansion, it's the reverse of that. It doesn't get wider, it gets narrower. See, that's maybe you have a better context for that. For all of you, that's a rite of passage when you become parents, having to drag your little kids to Disney. Me going on It's a Small World like 10 times. Oh, my boys were better. Space Mountain, baby. I'm screaming in fear. Let's go again, Dad. They just want to see me turn around and throw up. That's exactly what they want to do. May the good Lord bless you with children like that. Okay, and so here it is. So the actin are to the Z disc. The myosin are indirectly attached. You will see that in a minute. And so this interesting, here's the hexagonal arrangement. So really, this is important. Before I get into what's going on with it, I know we're running low on time. The I bands, why the light passes through it, they're just a thin filaments. The H zone, the I bands don't extend. Beg your pardon, the actin does not extend to this M midline area or H because it looks like a letter H. Doesn't matter. because I really don't ask a whole lot about that. Okay. Effectively, an M has a different name. It's got a fancy name called myomesin. That's right where they make it M. And so as you can see there, the H and the M, it's only the thick, no overlap. But when you see the A band, now you can see that neat arrangement of a thick surrounded hexagonally by thin filaments which are shared. Why effectively the ratio is about 2 to 1. And so that's where you begin. So if you took a section here, bang, like that. Here in that M or midline area, here the H zone. Again, there's not a whole lot overlapping. And the I, there certainly isn't. We're going to learn about this. It's called titin, Titin. We talk about elasticity. One of the characteristics of muscle is a protein that's arranged like a spring. And so when it comes back. So when you stretch a muscle, it can rebound quickly. Remember I was telling you a little bit about those tendons that kind of, that's kind of how those things work. When you stretch something, it responds reflexly. I will stop here. This is enough. Every one of these talks we're going to have for the next about 2 weeks is going to have this kind of abundance of information. This is why I would recommend to you to go over this stuff tonight or tomorrow when I send you this recording, so you got a handle on it. Thank you.